Okay, welcome back. And if you take a look at the screen here, we're doing the next lecture. We stopped on the last one. It was a kind of a good stopping point. We had our transformer. So we had kind of the standalone or open frame transformer that we had plugged into our system. And then we decided we're going to switch that to a PCB transformer that could solder into a PCB. And one of those looked like this right here. Hopefully you can see that. There we go. So we're going to use that Tamura part, which is already in the circuit. All right. So now what we're going to do is we're going to look at that, and we are now going to experiment around with inductive loads, a motor. And so what this lecture is going to be about, which is a lot of fun, is so say you design something and you've got a digital power supply. You got a couple of them like the 7805 and this MC33269. So you got 5 volts, you got 3.3 volts, and you decide to hook a motor up to one of these supplies. All right, so it seems reasonable, but then all of a sudden you hook it up to the supply, and maybe you've got the motor hooked up to the 5-volt supply or the 3.3-volt supply, and then maybe you've got your digital electronics to the 5 or the 3.3. Either way, the motor turns on, and then over a period of time, the processor keeps locking up, or the digital electronics fail. And the reason why is because you're inducing noise. That inductive load, that motor, as that motor is turning around, it's generating all kinds of noise and back EMF, which then gets pumped back into the voltage supply mains and dirties up everything. And those spikes can cause the processor to fail or the electronics to do something wrong. So what we're going to look at is how to clean that up. So we're going to analyze it on the oscilloscope. This is a lot of fun. And what our goal is when we're done, is when we turn that motor on and power it up, power it down really, really quick, rapidly, the power supplies stay nice and clean, or as clean as they can be. All right. So that's kind of what we're going to experiment on. Okay. So let's go directly to the bench and just get right into it and go from there. And we're just going to, in real time, kind of play with these different components and see what we can do to create noise and then get rid of noise. And we'll go back to the blackboard here and kind of show where we would add these components and so forth. All right. So I'll meet you at the bench. All right. And so as you can see, I've already plugged in this Tamura transformer. So because it's a little bit tricky to connect and push in there, I already did it and kind of made sure everything was good. So just to reiterate what we're doing here. So we've got AC is coming in here off this line right here, which let me show you this. So this is basically connected to our AC lines, and everything's off and unplugged. That's why I don't have gloves on right now. So this is our AC line coming in, and then I've made this cable. This is 14 gauge stranded wire, very, very good wire. And then brought that in, and then those AC lines go directly into the primary of this Tamura, right? And then I've got the primaries in parallel, and we've got it in the 115 voltage mode, 115 volts. Then the output, I've got the outputs in parallel as well, and I've got them connected under the transformers, so you can't really see them. And then the AC output, which is in this case going to be 6.3 volts, is then going to our bridge rectifier, and everything else is the same from there. All right. Now, some other stuff that I want you to look at is this. So I've kind of fabricated this cable here that you see, and this plugs in our AC lines here. Now, if this wire pops out while I'm doing something, I could possibly get touched here and hit my wrist or something like that. So what I wanted to show you, and again, you know, building things is all about fabrication, and you got to fabricate things cleanly and all that. So I wanted to show you some stuff here. So these little cable management clips, they come in all kinds of different sizes. And so what these do is basically they hold cables in place. So this one right here is a little bit too small to hold this cable, but this one will do. So the whole thing is I could just use a piece of tape, and I could just tape this down here like that. I could do that, right? But you know, the tape is, you know, not very reliable. So maybe I'll do some cable management. This is an AC line. I don't want to get shocked. So what I'm going to do is I'm just going to pull this double-sided tape off the back here. Throw that away, and then I'm going to kind of place this where I think would be a good position, maybe right about here. All right, push it down, And then I'm going to put this cable in here, and I am going to pinch it down in there. So now what's nice is this cable is nicely and cleanly tucked away here. It's managed. You know, this is not going to come up into me, and then these hot AC lines, which over here in the corner of the camera, are going to stay where they're going to stay, which is what we want. All right. So just a little trick there. Don't be afraid to put some cable management when you're doing these experiments to keep your wires away and all that. You can tape them or do these. Now, obviously, this is going to be really hard to get off of here, but you know, I'll probably use that again, so that's fine. I'll leave that there. All right. So let me get rid of these. Okay, so we've got our transformer here. And again, what I've done here is I put our probe leads for our oscilloscope. Here's the 3.3 volt supply, and here's the 5 volt supply on channel 1 and channel 2, so we can look at those voltages. So I got that. And then what else do we have here? Anything else interesting? Oh yeah. So here's the really cool thing that we're going to play with is, you know, I showed you some motors. And so these are a couple pump motors. And let's zoom in a little bit and let's take a look at these. So I don't have to bring them up to the camera. I can bring the camera down so that we can see things. Okay, so here's one of these pump motors right here, and hopefully you can see that. Yeah, I think you can. And so this is a micro air pump AP2P01 from Smart Pump Sync, 3 volts DC at 480 milliamperes. All right, 480, or is it 460? 460 milliamperes, 3 volts. So we only need 3 volts to drive this, but it's going to pull a lot of current. I mean, 460 milliamps, that's half an amp. But if you recall, our 3.3 supply can go up to 800 milliamperes. But our 5 volt supply, I believe, goes up to 500 milliamperes. All right, now, so, and then I've got another motor. And this one right here is, I believe this is not from the same company. And this one does not say what the voltage is on here, but it's roughly the same. It's a 3 volt supply, and this one probably pulls about 300 milliamperes, all right? So, but it'll run faster because it's smaller, right? So, okay, so the whole thing is these motors, as they run, are going to create a cyclic noise, all right? Because they're an inductive load. You're powering up an inductor. You're creating a magnetic field. The magnetic field's collapsing. That's what a motor does, right? And so we're going to have this noise generated, right? So the first thing that I want to do is I want to turn on the system, and I want to make sure the thing works, okay? So I'm going to go ahead and I'm going to plug this in. And because I'm going to be working and trying to get these components in here, I'm not going to put the gloves on, but the AC is over there pretty safe, and it's out of the way. So I'm not going to touch that, and I'm not going to get near these hot leads, all right? So I'm just going to be careful, but it would be better to wear the gloves, but it's just too hard to get parts in here. All right, so I'm going to go ahead and turn this on. And I turn it on, and we see we've got both of our supplies, the 3.3 and the 5 volt supply are good to go. All right, and so now we've got our system here, and so let's start doing a couple things. So let's confirm stuff. So the first thing that I want to do is, why don't we get one of our little probes, and I'm going to get our multimeter. And the first thing we're going to do is we're going to measure our voltages here, and we're going to see if everything is what we think it is. And we already know it is, but so I've got the multimeter here. And this gets really, really tough because you got cables everywhere, you got parts everywhere, and things just get smushed and crunched and slid off, and it's tough. So just bear with me here. But I like you to see things in real time. So I'm just going to go right here, and we're going to put this up here. And we're going to look at the 3.3 volt line. All right, so I plug that into the 3.3 volt line, and let's see if you can see that meter. There it is, 3.3. Okay, good. Let's do the 5 volt line. It's right under here. Put that in there. Okay, push that in. Looks good. Let me show it to you. 5 volts. Okay, and then over here on the left, I've got this line right here. And this is looking at the DC that's coming directly in from our wall transformer here, our bridge rectifier, and our smoothing capacitor, because I want to monitor that voltage there. And that's the only voltage we're going to monitor right now with the multimeter. So I'm going to kind of try and get this out of the way here so I can see it. And the reason why we want to see that is as we pull current from that transformer, that voltage is going to keep dropping and dropping and dropping. Now, remember that the 7805 requires a 2 volt voltage above the regulation voltage. So it requires 7 volts to maintain regulation. Remember that? at you know, high current or whatever. So as we drop voltage by pulling current from the transformer here to power this 3.3 volt supply, we're going to start messing up the 5 volts. All right, so it is going to start having trouble regulating. So that's one little thing to note there. Okay, so here we go. Let's have some fun. So what we're going to do is we are just going to connect a motor to this little switch right here. So I've got plus 3.3 coming into the switch, and then right from the switch, I'm going to take that 3.3, and then I'm going to connect another wire here to ground. So now this motor is basically going to get powered when I press this button. Okay, so let's see if it is. And it's a pump, so it pushes or it pulls. It's pushing. All right, so that's a pump, and it's very high frequency, very high RPM. All right, now let me put the other one in so you can see the difference. Here's the other one, same thing. These are color coded for polarity. So red is plus and there's minus. Okay, here we go. Here's this one. Much slower, right? Okay. All right, so let's go back to the fast one because it's more noisy. Okay, so we got this noisy motor. All right, so that's great. You hook that up and you're making some piece of hardware and you got a motor in there and everything's great. The 3.3 is also powering some digital electronics, and the 5 is, all right? And so you got the motor in there, you turn the motor on and something goes wrong. What goes wrong? So let's go take a look at the oscilloscope. All right, so over here on the oscilloscope, we've got channel 1, and let's turn on channel 2. All right, and the first thing I want to do is let's make sure both of these are on DC coupling. So we want to see DC on both of these, and then we got to change the vertical gain here so that we're 2 volts on the 5 volt supply. So it's 2 volts per division on the 5 volt supply. So you can see here's ground and then 1, 2.5 divisions. So there's our 5 volts, and let's get rid of that display. But our 3.3 is off the screen, so let's drop this down. There it is. So there's our 3.3, and it's 1 volt per vertical division. So 1, 2, 3, and about 3.5. So that looks good. So we're seeing the DC signals, which are staying there, and then you see this little noise on here. This is little AC noise riding on top of the DC signal. Okay, so now the question is, what happens if I turn that motor on? So I want you to think about it for a second. What do we think is going to happen here? So this motor is going to generate a lot of inductive noise on that 3.3 line. All right, so let's turn it on and see what happens. You see those little spikes on the yellow line? That's the 3.3 volt. And then look at the 5 volt line. See how it's wavering? We're not getting noise too much on the 5 volt line, right? We're not seeing that noise. All right, and this is the noise I'm talking about, these spikes. All right, we're not getting noise on the 5 volt, but we're seeing some wavering. So something's happening there. So let's speed this up. And again, this is going to be noisy. So what I'm going to do is maybe I'll cover this a little bit in something. All right, so now I'm going to change its frequency. And, okay, so now look at that 5 volt line. See that noise getting induced on there? So that's a waveform. That waveform is the motor waveform. So that is the motor cycling, and if we were to look at that frequency there, right, if we were to look at that, it would be the RPM rate of the motor. Now, here's another thing. Right when I power this thing up, the moment I power it up, I want you to watch both the signals. Watch how they dip and they gyrate. All right, look, did you see that? Look at the blue signal. See it dropping? All right, let me speed this up a little bit more. There we go. Or slow it down so you can see the event. There, look at that. So right when I power it up, boom. See that spike? Boom. All right, so the 5 volt for a second there really drops like a whole 2 volts, doesn't it? And then we just get constant noise on the 3.3 volt line, okay, which we do not like. All right, so first, what's going on with the 5 volt line? We're going to deal with that a little bit later, all right? But what I'm going to do now is I'm going to put the both traces in AC mode. So we're going to get rid of the DC offset. All right, there we go. So now all we're seeing is the AC signals. So the DC component is now gone, all right? And so now we'll just look at the noise on both of these signals here, okay? So now let's turn the motor on again, all right? So the 5-volt line has that sinusoidal noise on there, which you can't see because of the scale. So now what I'm going to do is I'm going to turn the scale way down to 200 millivolts and 200 millivolts. Okay, so now we're going to really start to see this noise, and you're going to be quite surprised. Okay, all right, so here we go. There we go. All right, so again, the 5-volt line is 200 millivolts per division, so I'm seeing about 400 millivolts of sinusoidal noise getting put on that. And I can let me slow this down a little bit more. Now you can see, look at that. Wow. All right. And then we're getting noise, just pure random noise and spikes on the 3.3. All right, now there we go. And I want you to see this there. So the 5-volt line has got about 400 millivolts of sinusoidal noise, and that sounds like it's the motor itself, right? So that looks like that's the motor frequency that the RPM is going at, giving us that noise. That's something's happening there. We're causing something to happen there. But we're getting all kinds of spiky inductive noise onto the 3.3 rail. Now, let's get rid of the second channel. Okay, so that's the 5-volt channel. Let's just turn that off. We don't need to look at that right now. Okay, let's focus on the 3.3. All right, so 3.3, here we go. Okay, wow, scary. Now let's change the scale here so we can see what's going on. All right, so now let's look, what kind of noise are we talking about? So we got 500 millivolts per division here, 500 millivolts. So every division is a volt. So if we go up and down, that's a whole volt. If we go up and down 2 of them, that's 2 volts, all right? So look at this noise. All right, now I'm going to stop this someplace in here, and we're just going to look at some of these. So look at some of these pulses. All right, so there's a pulse. That went up 1.5 volts. That went down, 7.75 volts. So we're talking about, 2 volts, maybe 3 volts up and down here of noise is getting modulated on that signal. And this is only a 3.3 volt supply. So we're spiking noise up and down, and the noise is going below ground. So the noise can go below ground. So this is really, 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 really bad. All right, so again, let's turn the oscilloscope on. Let's look at this noise. All right, so the question is, can we get rid of this noise? And there's more noise. This is continuous running, and then this is even worse when we fire this thing up. All right, so let's try and see. We can't really see it there, so we're gonna speed this up. And give me a second here. We'll put it about that. Now watch. Boom, boom. All right, so that's not too bad actually. But let's look at the DC. So let's also look at the DC here. I want to see this. There's the DC, and we're gonna. There we go. Okay. So now let's turn the motor on. Let's see what happens. So the AC noise is on top of it, but we've got it at 1 volt, so we're not going to see it that well. But I want to see if there's DC we're losing here. Not too bad. So it looks like we're just getting AC noise on top of the line. All right. So let's go back to AC. Let's put this back so we can see it here. Okay, and all right, so there's our signal, all right, and there's our noise, and let's change the scan rate here, and let's change the scale so we can really see the noise. There's 200 millivolt scale, and you can see the noise is just horrible. All right, so can we get rid of this noise? Let's go back to the bench and let's see if we can add a couple parts here and fix this thing up, okay? So let's go, let's go back to the blackboard and try and see if we can add. What we really have here is this. This is what we have. So, and I'm just gonna draw it right here. So we've got 3.3 volts here coming in, and we got that 3.3 volts, and then we've got a switch, a momentary switch, right? So those, how do those look like? They look like this. And then that momentary switch is coming down here, and it's going into this motor here, all right? And that's a horrible motor. Let me make that motor better. Make it a little bit bigger so you can see it. Okay. So here's this motor right here that this is going into, whatever symbol, there's different symbols for motors. And this is going directly to ground, all right? We flip the switch, current flows, right? The motor runs, and then what's happening is, as this motor, which is generating the current's generating a magnetic field, it's switching, doing all this, it's inducing noise, back on the 3.3 volt rail and pushing this back into the system. Okay, so what we want to do is, can we smooth this out? All right, so let's try a couple things. So first, let's do this. So right now, one thing, the moment we turn this motor on, it pulls a lot of current to start up. So motors have what's called their initial startup current, and then after that the current decreases because it's already running, right? So there's inertia already. But when the motor's at rest, right, it wants to stay at rest, so it needs more current to get going. So that's kind of the starting current, and then there's the running current, all right? And where is it going to get that current from? Well, it's got to go all the way back to the regulator. So first thing we're going to do is we're going to think about putting a big capacitor here, a storage capacitor. So this thing is charged, so when we turn this motor on, it pulls it from this capacitor. So maybe we make this 2200 microfarad. Then let's do another thing. Right over the motor, right here to ground, let's put a small capacitor, let's say 0.1 microfarad. All right, and that's going to get rid of some of the noise also that's being generated. So we're going to put this big capacitor here, and we'll put this little capacitor right here. Then let's turn the motor on. Let's see what kind of noise we get. All right, so let's go actually put those parts in and see what happens. All right, so we're back here on the bench, and what we're going to do is we're just going to do exactly what we just said that we were going to kind of model here. All right, so here's the motor, where the motor leads are, right? So what I'm going to do, first I'm going to put that 0.1 microfarad right across those motor leads, all right? So here is a 0.1 microfarad. And another thing I did, I've turned off the power here because as I'm moving my arm around, I don't want to touch the AC line. So here's a 0.1 microfarad. I'm going to put that right across our little power lead here. And this is all going to get a little bit small. There's not a whole lot of room here. All right, so I'll move the switch here like this for a second, and I'm going to put this right across here. Okay, good. Okay, and then here's the 3.3 feeder line that feeds the switch. So what I'm saying is, let's put a capacitor right here to ground so that when we feed, we don't have to go back through the rail all the way back to the regulator. We'll have a big 2200 microfarad to give us that initial startup current. Okay, so let's look here, and I think, yep, so this one is a 2200 microfarad 10 volt. 10 volts okay, we're running at 3.3 volt, but those spikes are pretty high, got to be careful, but they're smaller than 10. All right, this is polarized, so we're going to put ground to here, and let's see, we're going to have to bend this down a little bit, so we can kind of get this in here. So we're going to go ground to here. All right, there we go. I don't know if you just saw that LED flash for a second, because there was some charge on there, because I was experimenting, obviously. Okay, so now we've added our two things in here. So we got a big capacitor for our startup current to get this thing going. Then once it's rolling, we're going to basically have a noise filter, this little 0.1 microfarad, which is going to filter the noise, hopefully, and we're going to get some better results. Okay, so let's go ahead. Let's turn this thing on. All right. Okay, good. It's on. All right. Let's go ahead and let's press this power button, make sure it works. Okay, it's working. Okay, great. Now I want you to look at the oscilloscope, all right, and check this out. Okay, so we're at the oscilloscope here, and we're at 200 millivolts per division, okay? Let's go ahead and let's put that down to 100 millivolts. So let's really look at that noise. So there's nothing happening, and we can see there's a little teeny tiny bit of noise, but we got it at 100. So we're really going to scale and see any noise that we're generating, all right? So I'm going to turn the motor on and let it run in continuous mode. All right, now look how small our noise went down to. All right, so basically we're getting 25 millivolt spikes, if that. So now if I put it back down to 200 millivolts that we're looking at it before, we're not getting those big spikes anymore. They're gone. All right, now let's pulse this thing on and off, and let's see if we can get some big spikes that way. But now that big storage capacitor is going to save us. So here we go. All right, so look at that. We're still getting nice performance there, and you see that little dip a second every time we turn it on, right? It's dipping just a couple hundred millivolts, but it's getting that current from, it's getting that charge from that capacitor, and then we got almost no noise. All right, very, very little. So we could go, and let's look at this. Let's go to 50 millivolts. Now just sitting here, just the ambient noise. Now here's one little thing. Electronics in general, they generate, just picking stuff up, like 20 to 50 millivolts of noise. It's like you can't get rid of noise. So the noise that you're seeing right here is just a function of there's wires hanging out everywhere, these cables, this and that. It's almost impossible to get rid of that. So just keep that in mind. Now, here we go. I'm going to turn it on and let it continuous mode. And the amplitude, I'm seeing some spikes right now, probably 25 millivolts up and down. And now we'll hold that on. And now we can see the envelope, we're staying within a good plus and minus 50 millivolts. No more volts. Remember before we were like at a volt and a half. So we're at 50 millivolts now. And again, if I hit it and spike it, all right, we get that little spike there. That was 50 millivolts. And again, everything looks bad zoomed in, but we'll zoom out of this just a little bit. All right, there. There's like 1 volt scale. And now you can't even see it, right? So as we zoom in, 200 millivolt scale, you see a teeny tiny bit of noise. Let's get that noise so that we can see it a little bit better. We'll put it at 50 millivolts. All right, there we go. Let's go ahead, let's switch motors. So does our solution, we decide, hey, let's switch motors to this bigger motor. It's a little bit slower, and how does that look? So let's do that. And I'm going to switch this motor and get it in here. There we go. All right, here we go. Look at that. Barely anything out of that motor. So there's motor not on, there's motor on. Nothing. Looks great. Okay, so let's go back to the other motor because it's more noisy and we want a noisy source. Okay. All right. So let's go back to this other motor. Let's plug it in here. Okay. All right. Okay, so it looks like we've got the noise down to 50 millivolts plus and minus, and a couple times there it gets a little bit higher. All right, can we do better? Is there anything else we can do? All right, so again, we can keep working with capacitors and doing this and doing that. There's other things you can do, but let's go back to the blackboard on the computer here, and I'll show you something else we can add. Okay, so we're back here on the computer, and so there's something else we can do. So let's just erase some stuff up here to give ourselves some room. We don't need all this anymore, do we? All right, and matter of fact, we don't need this. Let's get rid of all this. Just give ourselves a little bit of room here. I'll keep all the circuitry so we can refer to it. Okay, so here's an inductor L, right? Now, what was the inductive reactance? Remember that? So what was the inductive reactance? So X sub L, what was that? Do you remember? It was 2 pi FL. And remember what X sub C was? If we had that, it would be 1 over 2 pi FC. Okay? But we don't need that. We just need this one. So this says that its impedance goes up proportional to the frequency. So remember, an inductor is basically a frequency-dependent resistor. So the higher the frequency, the more resistance or impedance, right? So we are trying to get rid of high-frequency noise. That noise is very high frequency. So what if we put an inductor in line with the power? So let's take a look over here. So our power's coming in through the 3.3 rail right here, right? So why don't we try this? So right where it's coming in, let's so here's the power coming in right here. Let's put an inductor right here. All right, and then this point right here will be 3.3 volts. So we're going to put an inductor L here. And so now what's going to happen is this inductor for DC, it's just going to pass it, but for AC, it's going to impede it. All right, so what's nice is that as this motor generates noise and it puts that noise, let's draw that noise here. So here comes this noise and it's all noisy coming through the system, right? And it gets to that inductor, and as a matter of fact, let's draw it bigger. Here's this noise, and it's happy, it hits that inductor, impedance, and that noise gets smaller. All right, so this right here, we could use like a 1 microhenry, a 2 microhenry. We could do math and we could model this, and we know how to do this. We know how to do complex impedance and compute for various frequencies, what the impedance is and so forth and all that, and we could do a bunch of calculations. But when you do real electronics, that is extremely time consuming. Now you can model it in the computer with simulation, but instead what you do is you use intuition a lot, and that's what you want to get here. You want to get some intuition, right? Just like when you fix a car, you're going to bolt something on, right? You take off the tires, take off the lug nuts, right? And you kind of have this feel for how much torque you need to apply those lug nuts to put that tire back on and keep that tire from falling off, right? You don't go get a torque wrench. I don't think anyone has ever got a torque wrench other than Indy pit crews to check how much torque they're putting on things. And they just use a tool that when it hits the right torque, it stops turning it, all right? Those impact wrenches, all right? Impact drivers. So same thing here. Let's use intuition. So what we want is we're going to use what's called a ferrite bead. And I told you about these before. And ferrite beads are inductors. All right, they've got a little piece of ferrite and they've got wire and they've got some coils through it, and they're an inductor, and they have different sizes, and they're spec'd at like maybe at 1 megahertz they're a 1 kilo ohm of resistance. All right, and we know that noise is pretty fast. All right, so it's up there in kilohertz and megahertz range, that noise that we're inducing. And so we're just going to put off the shelf little ferrite bead that I have a couple of right where we're looking at it right here, right into the feeder of this whole system, and we're going to see if that helps. So that's the first thing that we're going to do. And then there's one more idea we can try to get even less noise out, all right? But first, let's try this. So let's go put a ferrite bead in here and see how that helps. All right, we're back here on the bench, and I've got a couple of ferrite beads, and here they are here. Here's what they look like. So that's ferrite, which is, it's basically, you know, powdered iron, right? And then there's some wires. So we can get the camera to cooperate. There's some wires, okay, and that's it. And they're coiled in. Let's look at this on the zoom camera. All right, and let me see if it'll focus for us. Let me see if I can get it to focus. And it's not going to cooperate. It just likes that image in the back too much. Oh, there we go. So you can see. So see that? So it's coiled through there. Looks like 3 times. All right. So that's a ferrite bead. That's a big one. Then I got another one right here, and that's a real simple one. So it just has that ferrite going right around it. So obviously the other one's got more inductance, okay? All right, so let's go ahead and let's put this ferrite bead into the power lane there, all right? So I'm gonna turn this off, system's off. Now look at that, what's happening there? Oh, we had a bunch of charge inside the capacitor. That's why you saw that slow decrease. All right, so we wanna put this right in front of everything. So I want everything to go in through that ferrite bead. So we got to be careful here. So we're going to pull this down so we can see it a little bit better. All right. So I'm just going to kind of undo this a little bit and see what I'm doing here. All right. So let's do this. So what we're going to do is we're going to pull this out, and we are going to put the ferrite bead right here, like this. All right, and then that's going to give us trouble. So I'm going to try, what I'm going to try and do is I'm going to put the ferrite bead right here. And I don't want to bend it or break it. Okay, so there's a ferrite bead right there. Now what I'm going to do is I'm going to connect power to the ferrite bead right here. So there's our 3-3 going through the ferrite bead, because the ferrite bead is just too flimsy. Okay, all right. And so here's power going to the ferrite bead. Now I want to put the capacitor. I don't want to put it upstream. I could put it upstream, but we're not trying that. Let's put it downstream here. All right, so we're going to put it here. So here's ground, and then the other end of this is right here. Okay, make sure everything is good. Okay, so power goes into the ferrite bead, and then the capacitor as well. Capacitor charges to ground, and then when we flip the switch, we turn the system on. All right, let's connect our motor again. Let's get our small motor. All right, tricky. We get our small motor here and make sure it's the correct polarity. And I'm going to put the motor right here. All right, and we still got our capacitor there. And remember, that's only one capacitor, that 0.1 microfarad, and that's one big frequency band of noise it's taking care of. We could try a 0.01, we could try a 0.001, we could try a 1 microfarad, right? We could play around, and you know, you do. If you're going to do this professionally, you're going to sit here a couple hours, try things out, model it on the computer and all that, but these are some good tricks to try that should work. All right, and they already did. Okay, so I just turned the system on. You can see the lights are on. All right, so again, take a look at the oscilloscope. So this is just standard noise on that line. We're not even doing anything, and we're getting, 25 millivolts of noise in each direction. Okay, so we're already getting that noise. Now, here we go. So we're going to try turning this on. We're going to see if this helps a little bit. Now, we don't have anything to compare to right now, unfortunately. We just have to remember kind of what it was, but I remember, so I'll let you know. All right, so here we go. Wow, so look at that. So almost nothing. Every now and then I see a little spike. Every now and then I see a little spike, a couple big ones, but that's pretty good. Pretty good. All right, and then we could try switching the position of the ferrite bead and putting the capacitor, upstream. We could put the capacitor upstream here, so the capacitor is at the beginning of the ferrite bead, all right, instead of at the end of it. So let's give that a try, all right? So again, what I'm going to do is I'm going to power it down because the capacitor is going to be charged. I want to let it discharge. Okay, so it's discharged. So now what we're going to do is we're going to put the capacitor right here. So we don't have room here. So what I'm going to do is I'm going to have to move a couple things around. Being very careful here. I don't want to break this. This is just asking to be broken. All right. Okay. And then we're going to put our capacitor here right there. Okay. Now, capacitor and the ferrite beads. So the capacitor is upstream. Okay. So let's turn it on. Okay. Everything didn't explode, so we're good. All right. So I'm going to turn it on again, and we're going to look at our oscilloscope. So we look at the oscilloscope and nothing's on. You see the amount of noise, and now we turn it on. It's almost the same. Maybe a little spike once in a blue moon. So not much difference there, right? And again, if we lower the vertical division back down to 200 millivolts, we turn this on. It is clean as a whistle. Clean as a whistle. All right. Now let's finish off. Right now, I'm going to disconnect all this. So there it is. You can see it's very, very clean. All right. And then we get that little quick jump when it turns on sometimes. Very, very, very little noise. Okay. Very happy with that. Okay. So remember what that looks like. Now I'm going to turn it off, and we're going to really quick, we're going to pull this thing all apart. Okay. We're going to pull it apart. We're going to take this off. We're going to pull this capacitor out of here. All right. And then we're going to connect this thing up. We're going to put this like this. And because I just want you to see, I want you to remember. All right, and then here's plus, and here's ground. All right, ready? So now we got no filtering. Let's see what it looks like. And what did we do? What did we do? Well, we got to turn it on. Okay, here we go. Whoa! So we did indeed make a really nice filter system, and we cleaned that up, and that's great. That's what we want to do. All right. So now the problem with the 5 volt is we're pulling so much current. What we're doing is we're taking that regulator out of regulation. So we're just drawing too much current. Now, if we had a LDO, a low dropout regulator for the 5 volt, then we could look and see, are we inducing noise enough where the 5 volt supply is seeing noise, and then we could address that the same way we did this. We would put filters on it. We would put capacitor, we put inductor, and so forth. Right now, I want to go back to the computer, and I think we've got everything we wanted to do here. I think we did, a lot of cool stuff. So I think we're done here. Let's go to the computer, and I want to draw a couple things for you, a couple ideas that I want you to try when you're building power supplies, and to give them a try to reduce noise and just make good power supplies. All right. Oh, and one last thing that I want to talk about. We bring the power in. Let's get this on the screen here so you can see. So we bring the power in, and we'll draw this on the computer when we talk in a moment. But we've got the power coming in, through the AC line. All right. So if you make a real power supply and it's an AC power supply offline that plugs in, you are going to have a fuse here. And this is hot right now. Let's do this. I'm going to zoom out a little bit more here. All right. I'm going to zoom out. So here's the hot line right there in the corner. So well, these hot lines are going to come in here. We're going to have a fuse on this, some kind of fuse, right? And there's different kinds of fuses. They're what are called PTC, positive thermal coefficient, and when they break, they basically they get hot and then they melt and then they re-solidify. So they're really nice. Then there's little glass fuses, normal glass fuses you've probably seen. I don't think I have any here, but you're going to want to fuse that AC line. Now, if you're going to build AC power supplies that are offline with transformers and all that, there's a lot more you need to do. It's beyond the scope of this course right now. Maybe we'll do a scope on AC power supplies one of these days, but we'd want to put protection. We'd want to put those XY capacitors on there for filtering. We'd want to put a fuse and a bunch of other stuff. Now, let's assume that all this is from a wall adapter, something like that. So we don't mess with it. We just get a DC unregulated voltage, which we plug in to our regulators, all right? Even still, in those places, we can put fuses. We can put these what are called PTC fuses to protect things. Also, hey, what if there's a lightning strike or something and we get a big voltage spike coming through the transformer and all that? Well, we can put clamping diodes and what are called transient voltage suppressors, TVSs, V is in Victor, S is in Sam, T is in Terry, TVS. We can put those in front of those regulators as well, and I'll show you that when we go on the board. But what those do is clamp the voltage, so if we ever get a really high spike voltage because of a transient due to a lightning strike or something, it won't damage our power supply and of course damage our computer downstream that our power supply is powering, all right? So anyway, let's go back to the blackboard on the computer there, and let's look at some of these other things, and we're going to kind of wrap it up with that. So anyway, so that was a lot of fun. So I will meet you back at the computer. Okay, so we're back here on the computer, and the first thing is, all right, we got this. Let's just erase this, and let's kind of summarize what we're talking about here. So, let's do this. All right. So we've got a 3-pin regulator we've been talking about here. Here's our 3-pin regulator. All right, and we can draw that. Let's just draw that in a little bit of a different color here for fun. Here is our regulator, and we don't know what voltage this is regulating, right? It could be anything, but we'll just say it's like a 5-volt regulator. All right, and it could be just a standard linear regulator, or it could be an LDO. And I'm going to tell you I want you to use LDOs. Okay, they're just better, more efficient, less heat, all that, and only a little bit more expensive. So you're going to use an LDO, and that means that we can probably maintain regulation if this thing is like 5.2 volts or 5.3 volts, but it surely doesn't need to be 7 or 8 volts or something like that. So the whole point is we can have that low dropout. Okay. All right, so this is kind of what we're talking about, and over here we've got our V in, and if this is a 5-volt, maybe this is anywhere from 6 to 12 volts typically, right? And that's a wall wart. I don't know where that's coming from. It's coming from someplace, and it's DC. It's unregulated, all right? It's just DC. It's maybe a smoothing capacitor, a bridge rectifier, all that, but it's DC unregulated. Out here we've got V out, and we've got 5 volts regulated, right? It's regulated. That's the whole point. That's what this is, regulated. Okay. Okay, so that's kind of what we have, and then bare minimum we want to have a couple capacitors here. All right. That's what the bare minimum is in many of these designs, and they say whatever they are. But what I'm telling you is I want to see, in general, I want to see like a 10 to 47 microfarad big one. I want to see a 10 to 47 microfarad big capacitor. Then I want to see also a smaller one for noise like this, and I want to see this is going to be 0.01 to 0.1 microfarad. You can play with that. And again, over here, for noise, again, 0.01 to 0.1 microfarad, all right? So we got these 4 capacitors, all right, between V in and V out, all right? Now, what else do we want to put in here? So let's add some other stuff, okay? So the other thing that we're going to add here is this. We are going to add some ferrite beads, all right? And all kinds of analysis has been done, and this really helps. So we're going to put a ferrite bead there, and we're going to put a ferrite bead right there. So these are ferrite beads and ferrite bead. Okay, and here's our V out again. So now what these are going to do is these are going to reduce noise coming into the system, coming into the regulator, and then also, so whatever noise comes in is now going to get dampened by this ferrite beads, so that the output is going to be real clean. We're going to hit it again with another one, and moreover, if noise comes in this direction, right, this will dampen it, right? And then if it tries to get back through the regulator and back out here, because maybe here this is also going to another supply. So I want to make sure any noise getting injected into this is getting dampened, all right? So we'll put ferrite beads on both of them, all right? And so that's what we want to do there. Now, what are these other things that I was talking about? So I was talking about transient voltage suppressors and whatnot, right? Okay. So let's talk about what that is. So a TVS, transient voltage suppressor. So what that is, and we'll draw that in another color too, let's just be colorful today. So right here on the input, we're going to put a TVS, and there are many, many of these, all right? And they basically are diodes that are put in this opposite direction here. And these diodes are very similar to Zener diodes, so they'll have this kind of symbol. And this is a TVS, all right? And so what does that stand for? It stands for Transient Voltage Suppressor. All right, TVS. And so what this does is, so normally we're expecting 6 to 12 volts in here. We're all happy, right? We got our 6 to 12 volts, yada, yada, yada. Here it is. Then all of a sudden there's lightning strike. Lightning strike finds its way through everything, the transformers, the power strips and all that, and then it goes boom, goes crazy, right? And you got this big, transient voltage spike. This TVS is like a Zener diode, except this thing works in like nano or picoseconds. So it works super, super fast and shunts that voltage and clips it and clamps it so that your system doesn't see that. So it works super, super, super fast. This thing, an enormous amount of energy it can shunt for nanoseconds or picoseconds. So you put these TVSs on this input here to these DC lines, and that protects your entire system. So now it's kind of protected against voltage strikes and so forth and transient voltage, right? Now, this isn't going to help you against shorts and overcurrent situations. So now, say down at this end, here's our V out, right? Let's say that, this thing is rated at, say it's rated at 1 amp, okay? And you put a resistance on here that's so low that we pull an amp out, then maybe try and pull 1.25 amps out, something like that, right? And so what's going to happen is very quickly this thing is going to overheat, right? And it's going to shut down. Now, a lot of these will have automatic shutdowns and that kind of thing, right? But if it doesn't react fast enough or it doesn't have that feature, and you were to short this, you could potentially very quickly pull, like 5 to 10 amps through this, or more, 20 amps, something like that, who knows. And so in that case, what we might want is we might want to have some protection on the input, right, so that we don't pull all that current through here, all right? And so basically, if whatever's connected over here, I don't want to drag so much current through it that I cause damage to that as well. So then what we can put over here is something else, right? We can put a little fuse, and let me do this here. So now we can put and go here, and we can put a little fuse, and these things have different symbols, these little things here, these little fuses. But PTC fuse, positive thermal coefficient. And so what this means is as more and more current runs through here, this thing gets hotter and hotter and hotter. And when a certain amount of current surges through it, it gets so hot it melts and opens up, and then no more current flows. Then it re-solidifies and allows the circuit to run. So if the circuit pulls too much current for too long, it basically shuts the thing down, all right, and opens up. And that event might be 100 milliseconds to 10 seconds. So you can get these in different currents and different time constants. So basically you can say, hey, you can pull 5 amps, but you better not pull it for more than a couple seconds. You pull it for 5 or 10 seconds, and then this PTC is shutting you down, and it'll shut it off, right? So here's kind of, one version of a pretty full-featured power supply. So assuming this was an LDO regulator, we've got nice filtering on the input, we got nice filtering on the output, we got some ferrite beads on the input and output, we got high noise, we got noise protection, we got a TVS for transient voltage, and we got a PTC fuse so that we don't pull too much current. Now you build this on a board, you put a switch on it, you put an indicator LED, you got yourself a decent power supply. And when you look at other people's power supplies, you'll see, hey, they won't have, let's use a different color here. They won't have these other capacitors for noise. And these capacitors will be very small, like 1 microfarad, right? They won't have these these ferrite beads, right? They won't have this transient voltage suppression. They surely won't have this fuse. They'll basically have the bare minimum, just a couple caps, a regulator, and then, throw caution to the wind. That's not what you want to do. You want to build a little bit better stuff. And so here is how you want to do your linear and LDO regulators. And now, of course, these parts, you have to play with them and stuff and experiment and get some intuition. Again, we know how to model all this if we want to. We know the math now, right? But we don't really want to do all that. And you can also get on the bench and experiment. I took a motor, and maybe that's the exact motor I'm going to use in a product, right? So I sat there and I turned the thing on, boom, 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 and I look at the noise, and I put a couple parts in. I don't have any noise anymore, so I'm happy about that. So I'm done. Then I could go back and I could simulate it also if I wanted to. But anyway, so that's it. So that hopefully you had a lot of fun. And power supplies is an interest of mine. And it's always nice because if you know how to make a good power supply, then your hardware will work very well. And when transient events happen, motors, high current, etc., you're not going to mess everything else up because it's really hard to debug. Because if something happens from your power supply, you're like, you don't really know that it happens because it's a little transient event. And if you don't look and see those transient events, you might go look in the wrong direction and think your software is not working or firmware is not working, right? But really what's happening is your power supply is spiking all over the place and creating negative voltages, which tripped out your microcontroller and it went nuts, right? So anyway, so that's it. I think we're done with all this voltage regulation stuff. I'm pretty sure we are. So in the next lecture, we're going to swing back to transistors again. We're going to talk a little bit more about them. We already did a lot of material on them at the semiconductor level, and we did some experiments. We're just going to do a little bit more, just kind of go back to it again, and then after that, that'll wrap that up. All right. So anyway, I will see you in the next lecture, and that's it. Bye.